Good Lord. What are they doing here? God, they have changed things. Good morning, everybody. Is anyone already here? Wow, that has changed this Omlet Arcade. I don't think I'm going to do any further live streams on YouTube if they do these weird things. I can only apologize. And the lag is absolutely dreadful. So good morning, ladies and jelly beans. This is not going to work. This is not going to end very well. Luckily we have Teams. But for today I will do the live stream on YouTube. For other occasions I think I will move on to Teams. Because it seems more stable. God, they have changed these things. So today I'm not really going to do anything with the chat function. So I will make notes of the questions that you guys post in the chat, but I probably won't be able to ask you anything because the lag is absolutely dreadful. And I have this funny thing, this Omlet Arcade advertising, and PK12 Kent. God knows what this is. Just a quick sound check. Can you hear me all right? Can you hear me all right? Yes. Oh, that's good. Thank you, Carla. That's fantastic. And I also apologize in advance if the dogs start barking. It's not you, it's the dogs. So because of the restrictions for this live stream, as I said earlier, it's just dreadful lag. It doesn't seem to work properly, and I can only apologize. So we give people a few more minutes, and then what I'm going to do with you is I talk you through the theory behind this practical. And I understand that people found the practical quite challenging. Not so much the practical component, but actually what was behind. Am I right? Was the theory behind the practical challenging? Yeah, good dogs. Not so good when they break wind. I've barred them from being in the room. So we get 150 people. I didn't think so. Oh, that's good. Yeah, I think some people found it easier, some people found it more difficult. But I will tell you why it is really important to understand this concept of uncertainties. Oh, fantastic. So 2 more minutes. Yeah, I think, Astrid, you're absolutely right. What I found quite confusing when I started that topic was they all sound really, really similar. So you have a standard error or standard uncertainty, then you have got a combined standard uncertainty, you've got combined extended uncertainty, and all these things. So let me hopefully demystify things a little bit. And yes, there have been some issues with the program, and I apologize. There is only so much testing you can do beforehand. And sometimes you get some weird number combinations, which just simply throws the whole thing out of the water. We have, I think this is a novelty for the School of Biosciences today. We have actually 2-year cohorts, BI 600 and BI 532, together because both of you did the same practical and I set you the same tasks. For the BI 600, predominantly to get you introduced to that field before you start actually any lab-based projects. And also it is very, oh, well, I will tell you in a minute why it is important, the whole thing. Shall we make a start? Yeah, let's get started, okay? So, we've got 265 people watching. That's pretty much a record. Great, fantastic. Yes, let's get started. So, first of all, a most wonderful good morning, ladies and jelly beans. It's great to see you back at university. Although we are already in week 2, but obviously it has been a really, really weird year. Well, at least we are all sort of here, and that's a great thing. So you have done this practical, which is, for those of you who have done it, it was a straight repeat of what you have done in the first year. But in the first year, and the new first year students will do the same practical, but in a slightly different format. In the first year, we wanted you to get to grips with the equipment, with the pipettes, etc., etc. Whereas the focus of this practical for both final year and second year was to introduce you to the topic of metrology. And in case you wonder, metrology doesn't have anything to do with the weather. This is meteorology. Metrology is basically the science of making measurements. And why is this important? So far, most people are used to, when they do science, they are used to taking what is called a point estimate. A point estimate. So, for example, they measure blood glucose levels, and they find it's, let's say, 2.3 millimolar. And they say, all right, so I got this value, and I got this determined. I did that several times. I can do some statistics with it. And this is the value that I measure. But what metrology does is actually it brings home the point that every measurement that we do has an uncertainty. So we can indicate that plus minus an uncertainty. And this uncertainty can come from different areas. It can come from the tools that we use. It can come from the method that we use. And of course, it can come from the way we sample the results. And it is therefore absolutely essential to understand how these uncertainties come together in a way. And why is it important? Well, if you go, for example, into for example, clinical trials. So in clinical trials, and I can predict that a number of you will choose to go into this area, clinical trials, you will explore how efficient, how good a certain drug is. So you can say, right, this drug has this efficacy, and that would be your point estimate. But then, in order to get this drug approved by the FDA, you would also have to follow regulatory standards. And one of the key regulatory standards is actually the uncertainty. How good is the drug? Point estimate and the uncertainty of how good the drug is. So this is required by the regulatory bodies, that you determine the uncertainty of your measurements. The other thing is, this uncertainty can actually decide over life and death, if you like. So if we look at the current situation, you are all familiar with the dreaded R factor for the virus spread. And just as a side note, the R factor has nothing to do with the correlation coefficient. The R factor is a measurement of how much the infection spreads. And we basically have three scenarios. The infection can decline. So that is when the R factor is smaller than 0. That's an exponential decline. It can be at an equilibrium. So that is when the infection is sort of stable, when the R factor is equal to 1. And the infection can spread exponentially when the R factor is larger than, so I should say here 1, that should be 1, when the infection is larger than 1. So, and we can measure the R factor, the infection rate, for a sample that we take, but we need to be careful with the sampling. Yes, it is recorded. It is on YouTube, so it will be recorded. So we need to be careful with our sample. If we, for example, just take samples from people working in the NHS, we probably will find that we have a fairly high R factor there. If, on the other hand, we have an R factor that is, we take from people who have been in isolation for the last 6 months or so, then we would find something like that. So we bring in uncertainties from our sample, how we sample. So we could have an R factor of larger than 1 or smaller than 1. And this can be just very small, this uncertainty. And yet, in both cases, larger than 1 or smaller than 1, we would take very different approaches. It also depends on how good our method and how good our tools are in order to detect, for example, an infection. So that is why we need uncertainties and why we always have to indicate what the uncertainty is. Now we have what is generally known as type A uncertainty, and this is when we actually carry out measurements. And do samples. Type B measurements, or type B uncertainties, I should say. This is when we look at the method, when we look at the measuring equipment and try to figure out what are the limitations of measurements from theory or from manufacturer's specifications. So in this and type B, we not necessarily have to do the measurements ourselves. Oh yes, thank you very much for the hint. Please don't forget the attendance recording, although I'm not entirely sure how useful this is, but please make sure that you record your attendance so that we know that you have engaged. Right, now let's look at the type B uncertainties first. Every time we make a measurement, we have an uncertainty in our in this measurement, just simply coming from the device. And we usually distinguish between a digital device and its uncertainty. And this is one of the things that a digital device has is the display uncertainty. And you experience the display uncertainty. It's the display. It depends on how well we can actually read the display. And you have seen it. I think I gave the example of the banana of 99 grams on a balance that can weigh up to 1 gram, where the display is 1 gram. So it could be anything between 98.5 gram and 99.5 gram on the display. And we have no way of knowing where actually the true value sits. So it can't be anywhere in here. And therefore, because we have no idea where the true value is, and therefore we use a distribution which is indicated like that. Here are the values. And here are basically the limits, 98.5 and here is 99.5. And we assume in the middle that is the true value, that's the 99. And this is what is called an uninformed distribution, or because we have no information where our value is in there. We know it is bounded by these end parts, but other than that, we have no idea. So uninformed, or it's also called a uniform distribution. And the characteristic of a uniform distribution is that it is characterized by the mean, that's here the mean, in between here, and it also has a standard deviation of the resolution divided by 2 times 1 over square root 3. Yeah, I just noticed that the bloody cat is there. I don't know where it comes from. I don't know where the cat comes from. It's it's a new thing. That's why I'm not doing any live streams on YouTube anymore, because it's so annoying. Okay, so that's the standard deviation for a uniform distribution. If, however, we have an analog device, we usually, like a pipette or something like that, we usually have an idea where actually our measurement is located. So we can draw it like that. And this point here, this middle point here, that is actually, if you like, that's the mode of what we read. And the mode and the standard deviation for such a triangular distribution is given as the half of the resolution times 1 over square root 6. Now people have asked me, where do these square root 3, where do these square root 6 come from? And the answer is, they are just from the mathematics of these distributions. So we just have to accept them. You can, if you are more mathematically advanced than I am, you can work out what these numbers are. But, you know, if you don't have anything else to do, do it. Okay, so these are in general our type B errors, at least those that we can easily identify. Now I've used the word error here, although I really don't like it. I better scratch it out, because the word error implies that we made a mistake. But we are not making mistakes. This is just simply something that is inherent in the way we do science. So I rather prefer the phrase type B uncertainty. Yes, type B uncertainty. I must learn to avoid the bloody cat. So an uncertainty is not something that we can avoid in a way. And it's the same with type A. And if you remember the statistics sessions, at least in BI 308, we were talking about sampling errors. Sampling errors. This is when we just simply take some samples and try to make some predictions from these samples. But effectively, if we take a slightly different sample, we would get a different statistics. And again, I don't like the word error in it because there is no error in it. I would like to call it sampling uncertainty. And it's nothing that we can do to avoid sampling uncertainty. It is there. It is almost a little bit like herpes. You know, you got it. It's just, you can't avoid it. Whenever you do any sampling, you get sampling uncertainty. And we are going to have a lot of fun when we are looking at two-dimensional sampling, which we are going to do in one of the sessions then later on, when we actually work not in one dimension like you have done here with just sampling one parameter, i.e. the weight, but when we look at sampling two parameters, when we have linear regression. Well, 89% of the population in the Western world have herpes. Some of them are asymptomatic, others get these little cold sores, which is caused by the herpes virus, actually, when they are stressed, or UV or something like that. Okay. So, sampling uncertainty and, for example, display uncertainty. So how do we deal with these uncertainties? For example, you took a measurement at 0, so you tare, you set your balance to 0 with the tube on it, then press 0. But again, we have an uncertainty here. The balance shows you 0 plus minus the display uncertainty. And I should say this is a standard uncertainty. And then you added water to the tube and you got a weight, but again, plus minus the display standard uncertainty. So what you're doing is when you determine the weight of something, you actually do the calculation of the actual weight, or I should probably call it mass, minus the reading at 0, which is 0. So you do, in a way, you do a subtraction here. And that's very easy because for the point estimate, a mass minus 0 still gives you the mass that you are looking at, or the weight, or whatever you want to call it. But how do we deal with the standard uncertainties? And it turns out we can't just simply take these uncertainties and add them up. For uncertainties, there is a different rule. So if we want to combine uncertainties, and again, I should say combine standard uncertainties, we have to take a slightly different approach. What we have to say is, we have one uncertainty, and we can use linear algebra actually, where we are dealing with vectors. I'm not going into vector calculations in theory, and I don't expect you to learn that, but see the standard uncertainty, one of the standard uncertainties, as a vector, and I indicate it like that with an arrow. It has a direction and it has a certain length. So that is the uncertainty 1. The uncertainty 2 goes in a different direction, and it would look like that. So that would be the uncertainty 2 for our second measurement. And again, it has a direction and it has a certain magnitude. It has the vector has a length in it. And what we are now looking for is actually what is the combined uncertainty, and let's call that uncertainty combined. What is the combined uncertainty? And you know how you can calculate that. What would be, let's see how big the lag is, what would be the best way of calculating this UC? And that is a question now for you, because I'm talking all the time. How can we calculate UC? What's the key word here, how you can calculate that? Absolutely right, guys. You rock it. It's the Pythagoras. And we can say the combined uncertainty UC squared is nothing else but U1 squared plus U2 squared. That's the combined uncertainty. And that is, no, it's not the Nernst equation. And that is where a lot of people, in a way, fall over. Because they say, wait a moment, we have just subtracted things. Why should we add the squares of the uncertainties? It doesn't make sense. But if you think about it, you have an uncertainty and then you do an operation and you get, you increase the uncertainty, right? By just doing an operation. In other words, and we can write this, of course, the UC as square root of U1 squared plus U2 squared. And that is actually how you calculate a combined uncertainty. Now I have to say, this only works if you add or subtract two values with uncertainties. This is only correct if you add or subtract values with uncertainties. If you have to multiply or divide them, you can't really, you have to do an additional step to that, because these uncertainties that we're dealing with here are called the absolute uncertainties. And an absolute uncertainty has the same unit as what we measure, the measurand. Has the same unit as the measurand. And that's the absolute uncertainty. If we have to multiply or divide two values with uncertainties, what we need to use in this case is we need to use what is called the relative uncertainty. Relative uncertainties. And this relative uncertainty would be a percentage. So we could convert the absolute uncertainty into a relative uncertainty just simply by taking the absolute uncertainty divided by the measurand that we measure and multiply it by 100. So then we would get, for example, mass plus minus, let's say, 2%. So you see, the uncertainty no longer has the same unit. Here the unit would be gram. It has no longer the same unit. It has the unit basically percentage. And that is what we need to use when we multiply or divide two values. We need then the relative uncertainty, but this calculation step is not terribly demanding, I would say. So I hope this makes sense for that. So let's go back to when we subtract, for example, two masses or two volumes or something like that. And what we can do is we can say, for example, we have a volume. Let's take a volume 1 plus minus an uncertainty 1. And we remove from that, so take out, remove volume 2 plus minus an uncertainty 2. So we have, or we add something. It doesn't matter because adding and subtracting always has the same uncertainty equation. Now, what we get is actually a new distribution. And regardless of what distribution we had in the first place for our standard uncertainty, so maybe we had a uniform distribution here and another uniform distribution here. If we do something like that, we end up with a new distribution which, when we combine uniform plus uniform, we inevitably always end up with a normal distribution. So we do an operation where we have a standard uncertainty which is derived from a uniform distribution, and we have another standard uncertainty, again derived from a uniform distribution. We do this operation and we get a new uncertainty, a combined uncertainty, combined uncertainty which follows a normal distribution. I am not aware of any other circumstances where we don't end up with a normal distribution. And that is why a normal distribution is so important to understand. So what we get here when we take some volumes, when we subtract some volumes, or when we add some volumes, it's exactly the same thing. What we get, and I have to get the cat out of the way. What we get will be a normal distribution. This normal distribution is centered around the mean, and in this case the mean would be volume 1 minus volume 2. Or if we add them, it would be volume 1 plus volume 2. And we get a combined standard deviation, and we get a standard deviation. The standard deviation for this normal distribution, this is the combined standard uncertainties. This is the combined standard uncertainties. So I draw this like that. These are the combined standard uncertainty. This one here. And this combined standard uncertainty, that was our UC, which was given by the square root, that's from the Pythagoras, uncertainty 1 squared plus, and it's always plus, uncertainty 2 squared. That's the combined standard uncertainty that we get here. Combined because we just simply combine these individual single standard uncertainties. So, because we know it is a normal distribution, or it's very close to a normal distribution, this new distribution that we get for the difference or the addition of the volumes. And I think in your example, in the what you did, you added volumes with the pipette several times. So what you did for the final volume was you added not just 2 of these, you added I think 5 volumes. So your combined standard uncertainty, when you did that 5 times, would have been U1 squared plus U2 squared plus U3 squared plus U4 squared plus U5 squared. So these were all the standard uncertainties for the volumes that you added. And since they were all the same, you could have written it as square root of 5 times U squared. And that's quite easy to calculate because that is the same as U times square root 5, actually. So for those of you who wondered where this came from. So we can combine as many standard uncertainties as we like, and we will always get back a standard uncertainty, a combined standard uncertainty. Now, when we do a sample, actually, when we take samples, we also get a normal distribution. So that would be for samples. And basically that would be type A uncertainties, where we sample something. Here, this normal distribution is centered around the mean of our samples. So the mean of the weights. And again, we have a standard uncertainty for, oh, that should be symmetrical. Oh, let's do it like that. So this standard uncertainty for type A is given by what you have already learned in the first year. That is the standard error of the mean, which is given as the standard deviation, standard sample deviation, and I write that here, standard sample deviation, or sample standard deviation, divided by square root n, and square root n is the number of measurements that you take. That's in both cases, that is what this standard deviation of our new distribution is. And of course, we can combine, because we are all standard, we can also combine, we can make a new combination. You see, we can do a combination of the type A uncertainty squared plus the type B uncertainty squared. So if we want to combine that, we can combine whatever we want as long as we are in the standard format. Okay, now if we look at this resulting normal distribution that we get, and I draw again a normal distribution, I really like that. I love normal distributions because they're so normal. So here we have our normal distribution around mu. We have one standard deviation to the right and one standard deviation to the left. So that is our standard deviation. And now I want to know from you how much of our data are within this one standard deviation range. How much of the data are in this 1 sigma range? 1 sigma range covers for a normal distribution. 1 sigma range covers how much? Of the data. Absolutely right. It's 68%. So this means that when we follow this procedure, our combined standard uncertainties, you see, the combined standard uncertainties cover, can't even spell, cover 68% of all cases. But I mean, 68%, it's not even a first, is it? So we want to do a little bit better than that. And therefore, what do we need to do if we want a higher coverage? And that is usually expressed with a factor k, which is called the coverage factor, k, coverage factor. What if we want to have 95% of all cases covered? How much do I need to extend this 1 sigma so that I get 95% of all cases? What do I need to multiply? Indeed, and people have put it up, I need to define the 2 sigma range. Because the 2 sigma range, probably somewhere here, the 2 sigma range, this is another sigma here, this other sigma range, this now gives me 95% coverage. So that is now 95% coverage. So all I need to do really to get from my standard combined uncertainty to the expanded combined, because we have combined things, uncertainty is just simply times the standard combined uncertainty by factor 2. Or if you are a stickler for details, it's not 2, it is actually 1.96. Well, it doesn't really matter. 2 is absolutely fine. We are now in a position to say that we have done a measurement, we have combined all our uncertainty, be it type A, where we did some sampling, where we did some measurements, or be it from just looking at the specifications, looking at the display, determine the resolution, determine how accurately we actually can measure. And we got these combined uncertainties, and now we can say our measurement is the point estimate plus minus the extended or expanded uncertainty. Okay? And the expanded uncertainty is just simply 2 times the standard of the combined uncertainty that we measured earlier. Now what we can do, of course, is we can check out how close are we actually to a preset value. So if we know actually the actual value of something, the actual value of a measurement, the true, or maybe I should say the true value of a measurement, if I know that by some way, so for example, I know that it should be 20 microliter, that should be, let's say, or 200 microliter, that should be the true value. I can now say, right, what I can do is I take my actual value, plus minus the uncertainty, minus the true value. And I can write this as actual value minus the true value. And usually I don't care really which one is bigger, so I take the absolute of that. Emily, spot on. This is exactly the definition. The coverage factor tells us how many standard deviations I go away from the mean. So, actual value minus the true value, I don't care which one is bigger, plus minus uncertainty, and that is the extended uncertainty. So what I can do now is I can calculate this value and I can try to figure out if this value is actually covered by this extended uncertainty, and I probably should say expanded uncertainty. So let's say I have, what shall we say, 200, say 220, and the true value should be 200. So the difference, of course, is 20. Now, if my expanded, so that's the difference here, and if my expanded uncertainty is, let's say, 10, whatever units, let's say microliters, I have the following scenario. I take the difference, and again, I have another normal distribution here. So here is my distribution. It is centered around this difference here. This would be 20. This is the difference between the actual and the expected value, or actual value and true value. So this is the difference. My expanded standard deviation, and that is the 95% coverage. In this case, that is the 10 microliter. And now I can say, right, does this value actually, does my measurement include the value of 0? So I can ask, does it include 0? Does it include 0? Why do I want 0 to be included? Because I want to know whether the difference potentially could be 0, whether there is no difference between the actual and the true value. Now in this case, 0 would be somewhere here. And you see, 0 is not within this 2 sigma range here that I calculated for my combined uncertainty. So, although I can't rule out that 0 might appear, it is unlikely. So I can say, because this calculation, when I do my difference minus, so the difference minus the 2 times combined uncertainties, that was the expanded uncertainty. If this is larger than 0, then I know that there is actually a difference between the true and the actual value. And of course, I could now try and calculate a p-value for that. I can just simply do a statistical test, a t-test, for example. If this difference is larger than 2 times the combined uncertainty and it's larger than 0, then there is a difference. There is actually a difference between the true value and the observed value, and the actual and the observed value. If there is no difference, let's for example do this scenario here. Here we've got, let's say, a difference of, let's say, 20 again, 20 microliter, but now our combined standard deviation for that would, let's say this is 40 now, the combined one, where 95% of the data are located. So we can do the 20 minus our 2 sigma range, 2 times sigma, and let's say this was 40. Now this is smaller than 0, so a difference of 0, which would probably be around here, a difference of 0 would not be totally unexpected. And therefore, in this case, we can say, right, we have no evidence that there is a difference between the true value and the observed value. So I think that was the theory behind all of that. And now the really important thing is that you want to know is, when do you have to hand in the whole thing? Am I right? Do you want to know that, when you need to hand in something? Shall I tell you when you need to hand it in? Since the whole exercise was you to get a bit of an understanding of uncertainties, I have decided that you don't have to hand in anything, because I'm a nice guy. Try to do the tasks. I'm aware that there are some issues with the program. As I said, that can happen. My apologies, but you don't have to hand in anything in hard copy or submit anything. Are you happy with that? Go in peace, but please go. I hope you enjoyed the session, and thank you very much for watching, despite the cat and all the crap. Take care, be good, and don't do anything I wouldn't do. Enjoy the rest of your day and your week, and I shall see you hopefully soon. I miss you guys.